Tonight, we're going to answer a question that sounds almost too simple to take seriously. What is actually holding the Earth up in space? It's one of those questions that feels like it has an obvious answer, right up until the moment you try to find it. The Earth is a ball of rock and metal, almost 13,000 kilometers across, weighing more than anything you could imagine. And it's racing through empty space at 107,000 kilometers per hour, without a single thing underneath it. No support around it, and no mechanism keeping it there. But here's what changes everything. The answer isn't what most people assume. It's not just gravity pulling the Earth toward the Sun, and it's not just momentum keeping it moving forward. It's a precise, almost impossibly delicate balance between competing forces that has been running without interruption for 4.5 billion years. By the end of tonight, you're going to understand exactly what that balance is, why it works, where it came from, and what would actually happen if it ever broke. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something you already know. You've seen a ball on a string swung in a circle. The person holding the string pulls inward. The ball wants to fly outward. Those two effects balance each other, and the ball traces a circle through the air. The moment you let go of the string, the ball doesn't continue in a circle. It flies off in a straight line. The moment the tension disappears, the ball no longer curves. That demonstration, as simple as it is, contains almost everything you need to understand what keeps the Earth in orbit. The Earth is the ball. Gravity is the string. And the straight line the Earth wants to travel is called inertia. The interplay between those two things, gravity pulling inward and inertia carrying the Earth forward, is what an orbit actually is. But saying it that way makes it sound like there's some kind of active negotiation happening. Like two forces are competing in real time, and the Earth has to keep the balance just right, or something goes wrong. The truth is both stranger and more elegant than that. The Earth isn't fighting gravity. It's falling because of it, and it keeps missing the ground. That's what an orbit is. Controlled, perpetual freefall. To understand why that works, you have to go back to a man who, by his own account, worked out the foundations of modern physics in roughly 18 months. Isaac Newton, in the mid-1600s, developed the first complete mathematical description of gravity. He wasn't the first person to notice that things fall, but he was the first to ask a question that turned out to be revolutionary. Why does the apple fall straight down, while the moon doesn't fall at all? Because they're both made of matter. They both respond to Earth's gravity. So, why does one drop and the other orbit? Newton's answer changed everything. The moon is falling, he said. It's just moving sideways, fast enough that by the time it falls, the Earth has curved away beneath it. Think about that carefully. The surface of the Earth isn't flat. It curves. If you fire a cannonball horizontally, it moves forward while gravity pulls it down. The faster you fire it, the farther it travels before it hits the ground. Fire it fast enough, and the ground curves away just as fast as the ball falls. The cannonball never hits the ground. It keeps falling, keeps missing, keeps going. It's in orbit. Newton described this exact scenario in his work, what's now called Newton's cannon, a thought experiment in which a cannon is placed on top of a mountain high enough to be above the atmosphere. Fire the cannonball with enough horizontal velocity, and it circles the Earth indefinitely. Not because something is pushing it, not because it has an engine, but because falling in a curved trajectory around a round planet, when you have enough sideways velocity, is geometrically identical to orbiting. The Earth orbits the Sun by exactly the same principle. The Sun's gravity pulls the Earth inward. The Earth's velocity carries it sideways. The two effects combine so that the Earth traces a near circular path around the Sun year after year. Nothing holds it up, because up doesn't mean what you think it means in space. In space, there is no up. There is only the geometry of the path that gravity and velocity together create. Newton didn't stop there. He formalized gravity into a precise mathematical law. Every object with mass attracts every other object with mass. The force between them is proportional to the product of their masses and inversely proportional to the square of the distance between them. Double the distance, and the gravitational pull drops to a quarter. Triple the distance, and it drops to a ninth. This inverse square relationship isn't arbitrary. It falls out naturally from geometry. Gravity spreads out through three-dimensional space in all directions, like light spreading from a lamp. The farther you get from the source, the more the same total amount of force is spread across a larger surface. And the surface area of a sphere grows as the square of the radius. So the force per unit area drops as the inverse square of the radius. Newton's law describes gravity with stunning accuracy for most of what we encounter. It's why we can launch satellites and predict exactly where they'll be months from now. It's why we can calculate the trajectory of a spacecraft launched in the 1970s and know precisely where it is today, billions of kilometers from the Sun. Voyager 1, launched in 1977, is now more than 23 billion kilometers from the Sun. We know where it is at any given moment to within a few hundred kilometers. Newton's gravity, combined with careful orbital mechanics calculations, is that precise. But Newton's gravity is not the final word. Now, here's where it gets more interesting. Because Newton's description is elegant, and it's accurate enough that we use it to calculate satellite trajectories today. But it's not the deepest description of what's actually happening. For that, you need Einstein. And Einstein's picture is genuinely weirder. In 1915, Albert Einstein published his general theory of relativity. It rewrote the nature of gravity from the ground up. For Newton, gravity was a force, a mysterious action at a distance, where one massive object somehow reached across empty space and pulled on another. Newton himself was uneasy about this. He wrote that the idea of one body acting on another at a distance through a vacuum, with nothing mediating the interaction, was so great an absurdity that he believed no man who had a competent faculty of thinking could ever fall into it. He described it, offered the mathematics, and declined to explain the mechanism. Einstein explained the mechanism. And the mechanism isn't a force at all. Gravity, according to general relativity, is not a pull. It's a curve. Mass bends space-time, not just space. Space-time, the four-dimensional fabric in which everything in the universe exists and moves. Every object with mass, every form of energy, distorts the geometry of space-time around it. The more massive the object, the greater the distortion. The Sun is so massive that it creates a significant curvature in the space-time around it, extending outward across billions of kilometers. And here's the key insight. In curved space-time, the natural, unforced path that any object follows isn't a straight line. It's a curve. Physicists call these paths geodesics. A geodesic is the equivalent of a straight line in curved space. It's the path of least resistance, the path an object takes when no forces are acting on it. When you drop an apple, it follows a geodesic in Earth's curved spacetime. When the Earth orbits the Sun, it follows a geodesic in the Sun's curved spacetime. In both cases, the object isn't being pulled by a force. It's simply following the natural shape of the space it's embedded in. The Earth isn't being dragged around the Sun against its will. It's coasting along the straightest possible path through a geometry that happens to be curved. That's what Einstein showed. Gravity isn't a force in the traditional sense. It's geometry. And the Earth's orbit around the Sun is just the Earth following the geometry of the universe around it. The distinction might sound philosophical, but it has real, testable, measured consequences. Newton's gravity is instantaneous. According to Newton, if you somehow moved the Sun, the Earth would feel the change immediately, at the same instant. That can't be right. Information can't travel faster than light. Einstein's gravity propagates at the speed of light. Disturbances in spacetime, changes in the curvature caused by moving masses, radiate outward as gravitational waves. We detected those waves for the first time in 2015. Two merging black holes, more than 1 billion light-years away, distorted spacetime as they spiraled together. That distortion propagated outward at the speed of light, arrived at Earth, and stretched and compressed the entire planet by less than 1/1,000,000th of the diameter of a proton. We measured it. The instruments that did this, the LIGO detectors in Louisiana and Washington State, are arguably the most sensitive measurement devices in human history. They detect changes in length, smaller than any other instrument ever built. The mirrors in the detector are among the most isolated objects on Earth, suspended on pendulums designed to filter out every vibration from earthquakes, ocean waves, and traffic. And what they measured was the rippling of the same space-time fabric that keeps the Earth in its orbit. That's not abstraction. It's physics, made real, made audible. The signal was converted to sound, a brief chirp. The final moments of two black holes merging 1 billion light-years away. Space-time ringing like a struck bell, detected by lasers stretched across 4-kilometer corridors in the American countryside. The same fundamental phenomenon, gravity as the shape of space-time, expressed at the grandest scale the universe produces, measured in one of the quietest rooms on Earth. But here's the question that naturally follows. If the Earth is just following the natural shape of space-time, why doesn't it spiral inward and merge with the Sun? The geometry of the Sun's space-time curves space toward the Sun. So shouldn't everything moving through that curved space eventually end up at the center? The answer is angular momentum. And this is one of the most profound conservation laws in all of physics. Angular momentum is the rotational equivalent of momentum. If you spin something, or if something moves in a curved path around a point, it has angular momentum. And angular momentum is conserved. In the absence of external torques, it cannot change. This is Noether's theorem at work, one of the most elegant results in all of theoretical physics. Emmy Noether. In 1915, the same year Einstein published general relativity, proved that every symmetry in the laws of nature corresponds to a conservation law. Rotational symmetry. The fact that the laws of physics look the same in every direction corresponds to conservation of angular momentum. It's not a rule that was imposed on the universe from outside. It emerges from the fact that there is no preferred direction in space. If the universe were somehow asymmetric, if physics worked differently depending on which way you faced, angular momentum wouldn't be conserved. But it does work the same in every direction. And so, angular momentum is conserved. The Earth has angular momentum because it's moving sideways relative to the Sun. It's not heading directly toward the Sun. It has a sideways component to its velocity. That sideways motion gives it angular momentum. And because angular momentum is conserved, that sideways motion can never go away on its own. Something would have to act on the Earth, exerting a torque to change its angular momentum. And in the near vacuum of interplanetary space, there's essentially nothing to do that. So the Earth's sideways motion persists. Not because anything is maintaining it. Not because it has an engine running, but because physics forbids it from stopping without a reason. The combination of that conserved sideways motion with the inward curvature of the Sun's gravitational field locks the Earth into an orbit that has been stable for 4.5 billion years. It's not being held up. It's not being supported. It's simply the result of two fundamental properties of the universe: the shape of space-time around massive objects and the conservation of angular momentum, doing what they always do. Now, where did the Earth's angular momentum come from in the first place? Because it didn't always exist. 4.5 billion years ago, the solar system didn't exist. What existed instead was a vast cloud of gas and dust drifting in the outer arm of the Milky Way. That cloud was mostly hydrogen and helium, the leftover material from earlier generations of stars, seeded with heavier elements forged in stellar cores and scattered by stellar explosions. The elements that make up the Earth, the iron in its core, the silicon in its mantle, the oxygen in its atmosphere, were all cooked inside stars that lived and ended before the Sun was born. Those stars processed hydrogen and helium into heavier elements through nuclear fusion, building carbon, nitrogen, oxygen, silicon, iron, and everything heavier through a sequence of fusion reactions in their cores. When they reached the end of their lives, they scattered those elements into space through stellar winds and supernova explosions. Supernovae, the explosive endings of massive stars, are the primary mechanism for distributing heavy elements throughout the galaxy. The cloud that became the solar system was enriched by generations of such events. This is not a poetic statement. It's a chemical fact, confirmed by isotopic analysis of meteorites, the most primitive material in the solar system. Certain radioactive isotopes present in early solar system material could only have been produced by a supernova that exploded shortly before the solar system formed. The ratios of those isotopes in ancient meteorites tell us that a nearby stellar explosion seeded the cloud with freshly synthesized heavy elements, and may even have provided the push that triggered its gravitational collapse. The cloud wasn't perfectly uniform. It had slight variations in density, regions where slightly more material had gathered due to the turbulent mixing of interstellar gas over millions of years. Gravity began to work on those density variations. Denser regions pulled surrounding material toward them. As the cloud contracted, something crucial happened. The cloud wasn't perfectly still. It had a slight overall rotation, the residual motion from the turbulent environment in which it formed, the gravitational jostling of nearby stars, and the passage of spiral arm density waves. As the cloud collapsed under gravity, that rotation sped up by a lot. Conservation of angular momentum again. When a rotating object contracts, its rotation rate increases proportionally. The same physics that makes a figure skater spin faster when they pull their arms in applies to collapsing clouds of interstellar gas. As the cloud shrank, it spun faster. As it spun faster, the centrifugal effects of the rotation resisted collapse in the plane perpendicular to the spin axis. Gravity could pull material inward easily along the rotation axis through the poles. But material in the equatorial plane was flung outward by the rotation as fast as gravity pulled it in. The result was a flattened disk of material orbiting a growing central mass. The central mass eventually became the Sun. The disk of material around it became the planets. And every bit of material in that disk was orbiting the proto-Sun because of the angular momentum inherited from the original slow rotation of the interstellar cloud. When the material in the disk clumped together under gravity to form the Earth, that orbital angular momentum was conserved. The Earth formed, already moving sideways, already in orbit. The angular momentum of the solar system has been building from the very first moment the cloud began to collapse, and it hasn't diminished since. So the Earth is orbiting because it was formed orbiting, and angular momentum conservation means it can't simply stop. But that still leaves a question that's worth pressing on. How stable is this arrangement, really? Because intuition might suggest that even a tiny perturbation, something nudging the Earth slightly off its path, could accumulate over billions of years into something significant. If you imagine balancing a marble on top of a dome, even the slightest nudge will send it rolling off. Is the Earth's orbit like that? Teetering on a knife edge, always one small push away from disaster? The answer is no. And understanding why requires looking at what kind of equilibrium an orbit actually is. An orbit isn't like a marble balanced on a dome, which physicists call an unstable equilibrium. It's more like a marble resting in the bottom of a bowl, a stable equilibrium where small perturbations don't accumulate, but instead oscillate around a central state. If something nudges the Earth slightly closer to the Sun's gravity gets slightly stronger. But the Earth's orbital velocity hasn't changed. Now the Earth has slightly more velocity than it needs for the orbit at that distance, so it swings back outward. It overshoots slightly, moves a bit farther from the Sun than before, where gravity is slightly weaker. Now it has slightly less velocity than needed and falls slightly inward again. The result is that the Earth oscillates gently around its ideal orbital path. The perturbation doesn't grow, it oscillates. The orbit is self-correcting in this sense. Not perfectly. Over very long timescales, the orbits of all the planets subtly influence each other through gravity. Jupiter's enormous mass, in particular, creates slow variations in Earth's orbit over cycles of tens of thousands to hundreds of thousands of years. These are called Milankovitch cycles, named after the Serbian astronomer Milutin Milankovic, who calculated them in the early 20th century. They're real and measurable, and they drive ice ages and warm periods in Earth's geological record. Milankovitch identified three main cyclical changes in Earth's orbital parameters. The first is eccentricity, how elliptical the Earth's orbit becomes as it's gently tugged by Jupiter and Saturn, which cycles over roughly 100,000 years. The second is obliquity, how much the Earth's axis is tilted relative to its orbital plane, which cycles over about 41,000 years. The third is precession, The slow wobble of the Earth's rotational axis, like a spinning top winding down, with a period of roughly 26,000 years. These cycles combine and interact, producing complex patterns in how much solar energy different parts of the Earth receive at different times of year. The geological record shows ice ages correlating with these cycles. When the northern hemisphere receives less solar energy in summer due to the combination of orbital parameters, snow and ice can survive the summer months and begin to accumulate year after year. As ice builds up, it reflects more sunlight back into space, a feedback that amplifies the cooling. Ice ages have covered much of the northern continents repeatedly over the last few million years. The cycles don't change the total energy Earth receives from the Sun by much. They change how that energy is distributed between hemispheres and between seasons. But distribution turns out to matter enormously for climate. The last ice age peaked about 20,000 years ago, when ice sheets covered much of North America and northern Europe. Sea levels were lower by about 120 meters. Land bridges existed where oceans are now. All of that climate variation traced back to the gentle gravitational influence of Jupiter, expressed through slow, rhythmic changes in the shape and orientation of Earth's orbit. None of these variations push the Earth into an unstable spiral. They're bounded oscillations. The Earth's orbit is chaotic in the technical mathematical sense, meaning that tiny changes in initial conditions lead to unpredictable differences over very long timescales. But it's not unstable. The difference matters. Chaotic means unpredictable in detail. Unstable means diverging catastrophically. The Earth's orbit is the former, not the latter. Models suggest it will remain in a roughly habitable zone around the Sun for at least another billion years, possibly much longer, before the Sun's increasing luminosity, not orbital mechanics, becomes the dominant threat to conditions on the surface. Now, let's think about the Earth in relation to its own motion, because the orbit around the Sun is only part of the story. The Earth is also rotating on its own axis, making one complete rotation every 23 hours and 56 minutes. Not 24 hours. The 4-minute discrepancy is real, and it matters. The 23 hours and 56-minute period is called the sidereal day. It's the time it takes for the Earth to rotate 360 degrees relative to the distant stars. The 24-hour day, called the solar day, is the time between one midday and the next. It's slightly longer because as the Earth rotates, it's also moving along its orbit around the Sun. So it has to rotate slightly more than 360 degrees to bring the Sun back to the same position in the sky. About 1 extra degree per day, matching the roughly 1 degree per day that Earth moves along its orbit. The difference adds up to about 4 minutes per day, 1 full extra rotation per year. Over a year, the Earth makes 366 sidereal rotations, but only 365 solar days. This is why the star patterns you see at night shift slowly from month to month. Orion is a winter constellation from the northern hemisphere, not because of the season itself, but because of where Earth is in its orbit, when Orion happens to be visible in the nighttime part of the sky, and the Earth is tilted 23.5 degrees relative to the plane of its orbit. Both of those facts, the rotation and the tilt, are consequences of the same violent early history that gave the Earth its angular momentum to begin with. The Earth formed from countless collisions between smaller bodies called planetesimals. These were rocky and metallic chunks, some the size of dust grains, some the size of small mountains, that aggregated together over tens of millions of years to build up the proto-Earth. Every single one of those collisions delivered angular momentum to the growing Earth, each one adding to or subtracting from the growing planet's rotation depending on the angle and direction of impact. The net result was a spin, a particular direction, a particular rate. And that spin has been carried forward ever since. But the single most significant event for the Earth's rotation was a specific collision late in the planet's formation. About 4.5 billion years ago, the proto-Earth was struck by a Mars-sized body that planetary scientists call Theia. The impact was oblique, not head-on. Theia struck at an angle. The collision was so energetic that it melted much of both bodies, vaporizing rock and metal, splashing enormous quantities of material into orbit around the Earth. That orbiting material, a ring of vaporized and molten rock, gradually cooled and coalesced into the Moon. The evidence for this giant impact hypothesis is compelling. The Moon has almost the same oxygen isotope ratios as the Earth, suggesting they formed from the same material pool. The Moon is unusually large relative to its parent planet compared to other large moons in the solar system. The Moon's iron core is small relative to its overall size, consistent with it forming mostly from the mantle material of both Theia and the proto-Earth. Most of the iron having already sunk to the cores of both bodies before the impact. Computer simulations of the collision reproduce the main features of the Earth-Moon system with reasonable accuracy. The impact itself delivered a massive jolt of angular momentum to the Earth, setting it spinning at what was almost certainly a much faster rate than today. Early Earth may have had a day of only 5 to 6 hours. The collision also set the Earth's spin axis at a tilt relative to its orbital plane, not perpendicular, tilted. And that tilt, that 23.5 degrees, is the reason we have seasons. The tilt means that as the Earth orbits the Sun, different hemispheres receive sunlight at different angles throughout the year. Northern summer, when the northern hemisphere tilts toward the Sun, receiving more direct light at a steeper angle. Northern winter, when it tilts away, receiving less light at a shallower angle. The seasons have nothing to do with the Earth being closer to or farther from the Sun. In fact, the Earth is slightly closer to the Sun in January than in July. It's purely the tilt. Purely a consequence of the Theia impact billions of years ago. There's something else worth understanding about what keeps the Earth positioned as it is. The Moon is not a passive object in all of this. The Moon plays an active role in stabilizing the Earth's rotational axis. Without the Moon, the Earth's axial tilt would wander chaotically over time. Mars, which has no large moon, only 2 tiny moons called Phobos and Deimos, has an axial tilt that has varied between roughly 15 and 35 degrees over hundreds of millions of years, possibly more, according to long-term computer simulations of the Martian orbit. Those variations drive dramatic climate swings on Mars, radically redistributing water ice between the poles and the mid-latitudes over long cycles. Earth's axial tilt, by contrast, varies only modestly over long periods, staying within a range of roughly 22 to 24.5 degrees, cycling with a period of about 41,000 years. The Moon acts as a gravitational stabilizer. Its tidal pull on the Earth's equatorial bulge, The slight thickening of the Earth at the equator caused by rotation exerts a torque that resists large changes in the axial tilt. The Moon is like a gyroscopic anchor for the Earth's orientation. Without it, our seasons would be erratic on geological timescales. Climate zones would shift dramatically and unpredictably over millions of years. The stability that has allowed complex life to evolve and persist over hundreds of millions of years may be at least partly a consequence of the Moon's stabilizing presence. And the Moon is there because of a catastrophic collision, a chance impact between a newborn planet and a wandering body. The stability of the Earth's environment is built on what appears to be an extraordinarily fortunate accident. Whether it was genuinely rare in the galaxy, or whether similar impacts commonly produce moons for rocky planets, is something we won't know until we understand exoplanetary system architectures much better. But there's a second aspect of the Moon's gravitational interaction with Earth that most people don't think about. The Moon is slowing the Earth's rotation. Gradually, imperceptibly by human standards, but measurably. The mechanism is tidal friction. As the Earth rotates, it drags the tidal bulges, the regions of ocean and crust, slightly raised by the Moon's gravity, forward with it. Because the Earth rotates faster than the Moon orbits, these tidal bulges are always slightly ahead of the Moon along the orbit. The Moon's gravity pulls back on these bulges, creating a slight braking torque on the Earth's rotation. Angular momentum must be conserved. So as the Earth loses rotational angular momentum, the Moon gains orbital angular momentum. The Moon's orbit slowly expands. The Moon is moving away from the Earth at a rate of about 3.8 centimeters per year. We know this with remarkable precision because the Apollo missions left retroreflectors on the lunar surface, small arrays of corner cube prisms designed specifically for this kind of long-term measurement. Scientists have been bouncing lasers off those reflectors from observatories on Earth and timing the round trip with extreme precision since the early 1970s. More than 50 years of measurements, accumulating into one of the most precise, long-term physical experiments ever conducted on astronomical scales. And the Earth's rotation is slowing by about 1.4 milliseconds per century. That sounds negligible. But over the history of the solar system, it adds up considerably. When the Earth was young, the day was much shorter. Estimates based on ancient tidal rhythms preserved in geological sediments suggest that around 450 million years ago, an Earth day was about 22 hours. Certain organisms, particularly corals and bivalves, preserve daily and annual growth rings in their hard parts. By counting those rings in fossil specimens and comparing daily ring counts against annual rings, scientists can estimate how many days were in a year at different points in Earth's history. The orbital period of the Earth, the year, hasn't changed significantly over geological time. But if there were more days per year in the past, each day must have been shorter. The data are consistent with a gradually slowing Earth. Go back to 3.5 billion years ago, and the day may have been as short as 6 to 12 hours. The young Earth was spinning dramatically faster. The Moon was much closer. The tides were much stronger. The sky would have been a very different place. The Moon, seen from the early Earth's surface, would have appeared much larger in the sky, perhaps 2 to 3 times the angular diameter we see today. The tidal forces would have been powerful enough to create enormous oceanic tides and even measurable tides in the solid rock of the crust. All of that tidal energy was slowly, steadily converted into heat through friction and radiated away, the rotational kinetic energy of the Earth bleeding off across billions of years. And with each passing year, the Earth spins fractionally slower and the Moon drifts fractionally farther away. In the very long run, given enough time, the Earth would eventually become tidally locked to the Moon, always showing the same face to it. The same process already locked the Moon's rotation to its orbit around Earth. That's why we always see the same side of the Moon. The far side isn't darker than the near side. It receives just as much sunlight. We just never see it from the ground, because the Moon's rotation and its orbital period were synchronized by tidal friction long ago. But the Sun is already evolving on a timescale that will change everything long before tidal locking of the Earth becomes relevant. The Sun will have expanded into a red giant and dramatically reshaped the inner solar system before the Earth's rotation slows enough to approach true tidal locking with the Moon. The endpoint of tidal friction, for us, is academic. The process is real and measurable. But other things will happen first. There's another question buried in all of this that deserves attention. Why is the Earth where it is? Not just in terms of orbital mechanics, but in terms of the Sun's gravity well. Why is the Earth specifically 150 million kilometers from the Sun rather than much closer, like Venus, or much farther, like Mars? The answer takes us back to the disk of material that surrounded the young Sun. The disk wasn't uniform. It had a temperature gradient. Close to the Sun, it was hot. Rock and metal could exist as solids, but gases and ices could not condense. Farther out, beyond what astronomers call the frost line, the disk was cool enough for water ice, carbon dioxide ice, and other volatile compounds to freeze out of the gas and become part of the solid material available for planet formation. The frost line in our early solar system was somewhere between 2 and 3 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun. The rocky planets, Mercury, Venus, Earth, and Mars, formed inside the frost line. They built themselves from rock and metal, the only materials that could remain solid in the inner disk. The gas giants formed beyond the frost line, where they had access to enormous amounts of ice that could help their solid cores grow large enough, fast enough, to gravitationally capture the abundant hydrogen and helium gas before the Sun's radiation blew that gas away. If a rocky core doesn't reach a critical mass, roughly 10 to 15 times the mass of Earth, before the gas disperses, it can never become a gas giant. Jupiter and Saturn made the cut. The Proto-Uranus and Proto-Neptune just barely did. The position of the Earth in the disk was determined by which region of the disk had the right density of material to aggregate, the right temperature to allow rocky condensation, and which planetesimals happened to be swept up in the growing Earth's gravitational catchment area. There's a degree of randomness to it. The final configuration of the solar system, with the planets in their current orbits, emerged from a chaotic process of collisions, gravitational interactions, and orbital migrations. The model that has come to dominate planetary science, developed in the early 2000s and called the Nice model after the French city where several of the researchers worked, suggests that the giant planets didn't always occupy their current positions. In the early solar system, Jupiter and Saturn were likely closer to the Sun than they are today. Their orbital interactions through a resonance crossing, when their orbital periods fell into a simple ratio with each other, destabilized the outer solar system. Jupiter moved outward slightly. Saturn moved outward significantly. Uranus and Neptune were scattered far outward, possibly even trading positions in the process. This orbital reshuffling sent shockwaves through the entire solar system. Enormous numbers of smaller bodies were scattered inward. A period known as the Late Heavy Bombardment, around 3.9 billion years ago, may have been the result of this orbital upheaval. During that period, the inner solar system was pelted with impacts far more intense than anything since. The ancient, heavily cratered surfaces of the Moon and Mercury preserve the scars of that era. Earth was hit too, but geological processes, including plate tectonics and erosion, have erased most of that early record. Some researchers have proposed that the late heavy bombardment may have delivered significant amounts of water and organic molecules to the early Earth, potentially contributing to the conditions that allowed life to begin. Others argue the evidence for a specific late bombardment, concentrated in a short window, is less clear than previously thought. The debate continues. What's clear is that the Earth's current position isn't the result of any kind of deliberate arrangement. It's the result of a chaotic, violent, statistically fortunate process that ended with a rocky planet of roughly the right mass in roughly the right location. 150 million kilometers from a stable middle-aged star, in a zone where liquid water can exist on the surface. In a solar system whose history left it with a large protective outer gas giant and a substantial moon. Small changes to the initial conditions might have produced a solar system with no habitable world at all, or one with several. We don't know which outcome is rare and which is common. That's one of the great open questions in planetary science. Let's come at the original question from a different direction now. The Earth is not just sitting still in the Sun's gravitational field. It's moving through the galaxy. The entire solar system is orbiting the center of the Milky Way. The center of the galaxy is in the direction of the constellation Sagittarius. At the center of the galaxy, about 26,000 light-years from us, sits Sagittarius A, a supermassive black hole with a mass of about 4 million times that of the Sun. We know this with extraordinary precision because of decades of observation tracking the orbits of stars near the galactic center. Those stars move on elliptical orbits around Sagittarius A that are governed by the same Newtonian and Einsteinian physics as the planets orbiting the Sun. The stars, nearest the center, called the stars, move at speeds of thousands of kilometers per second. Star S2, one of the most closely monitored, has an orbital period of just 16 years. The periapsis of its orbit, its closest approach to Sagittarius A, brings it within roughly 120 astronomical units of the black hole. At that distance, it moves at nearly 3% of the speed of light. These measurements have allowed astronomers to determine the mass of Sagittarius A with remarkable precision. The gravity of Sagittarius A, combined with the gravity of hundreds of billions of other stars and an enormous amount of dark matter in the galactic halo, holds the Milky Way together. The solar system orbits the galactic center. It takes roughly 225 million years to complete one orbit of the galaxy. One galactic year. The velocity of the solar system, relative to the galactic center, is approximately 220 kilometers per second. We're not stationary even on that scale. And the galaxy itself is moving. The Milky Way is falling toward the Andromeda Galaxy, pulled by their mutual gravity. In about 4 billion years, the two galaxies will begin to merge. A collision of galaxies that sounds catastrophic, but is in fact mostly a merging of vast, empty spaces punctuated by stars, so widely separated that actual stellar collisions will be exceedingly rare. The structure of both galaxies will be dramatically disrupted. Stars will be flung into wild new orbits by the interaction of the two galaxies' gravitational fields. The solar system may be ejected into a halo orbit around the combined galaxy. But the Earth's orbit around the Sun and the Sun's gravitational hold on the solar system will very likely survive the merger. The geometry of that orbit, the angular momentum, the gravitational balance, all of it persists, regardless of what the broader galactic environment does. There's motion nested within motion, all the way up. Earth orbiting the Sun. The Sun orbiting the galaxy falling toward Andromeda. The local group of galaxies, of which the Milky Way and Andromeda are the two largest members, being pulled toward a large concentration of mass called the Great Attractor, itself embedded in the Laniakea supercluster, a gravitationally connected region containing hundreds of thousands of galaxies and stretching over 500 million light-years. And all of it, at the largest scales, embedded in the expansion of the universe itself. The expansion doesn't overcome local gravity. Gravity still rules at the scales of planets, stars, and galaxies. The expansion only dominates at cosmological distances, where the density of matter is too low to hold things together gravitationally. But it means there is no absolute rest, no fixed point, no bedrock. Everything is moving relative to everything else, and the Earth's position in space is not a location so much as a trajectory. One embedded within trajectories, all the way out to the edge of the observable universe. Now let's look at the actual numbers more carefully, because the Earth's orbit around the Sun isn't quite as simple as a perfect circle. It's an ellipse, a slightly squashed oval. This was discovered by the German astronomer Johannes Kepler in the early 1600s, and it was one of the most consequential discoveries in the history of science. Kepler had access to the astronomical observations of Tycho Brahe, the most precise, naked-eye astronomical data ever collected. For 20 years, Tycho had meticulously tracked the positions of planets from his observatory Uraniborg on the island of Ben, off the coast of Denmark. He measured their positions to an accuracy of about 2 arc-minutes, far better than any previous observer, without the aid of a telescope, which hadn't been invented yet. Kepler tried for years to fit Tycho's data on Mars to a circular orbit. He couldn't make it work. No matter what circle he tried, the predictions were off by a few arc-minutes. Precisely the margin of Tycho's observational accuracy. Kepler trusted the data over the theory. He was willing to abandon the ancient assumption that the heavens moved in perfect circles, an assumption so deeply embedded in astronomical thought that it had gone unquestioned for 2,000 years, embedded in the cosmology of Aristotle and Ptolemy, and accepted across cultures and centuries. He abandoned the circle and tried other shapes. After years of exhausting calculation, doing it all by hand, without any mechanical aids, he found the answer. Ellipses. Mars follows an elliptical orbit with the Sun at one of the 2 focal points of the ellipse. And when Kepler applied the same principle to the other planets, everything fit. This became Kepler's first law. For Earth, the orbit is very close to circular. The eccentricity, the measure of how elliptical an orbit is only about 0.017 for Earth. That means, at its closest point to the Sun, called perihelion, Earth is about 147 million kilometers away. At its farthest, called aphelion, it's about 152 million kilometers away, a difference of roughly 5 million kilometers, about 3.5%. That's small enough that for most purposes, the orbit can be treated as circular. But it's measurably elliptical, and Kepler's discovery of this was crucial. A circular orbit is an idealization. The real universe doesn't produce perfect circles. It produces ellipses, because the conditions under which orbits form involve collisions, perturbations, and the gravitational tugs of other bodies. A perfect circle requires an exact balance between velocity and gravitational pull at every single point. The slightest deviation produces an ellipse. And in practice, slight deviations are inevitable. Kepler's second law is equally fascinating and less widely understood. He noticed that Mars didn't move at a constant speed around the Sun. It moved faster when closer to the Sun and slower when farther away. Kepler described this geometrically. A line connecting the planet to the Sun sweeps out equal areas in equal times. In practice, this means the Earth moves faster in January, near perihelion, than it does in July, near aphelion. The difference is real and measurable. At perihelion, Earth is moving at about 30.3 kilometers per second. At aphelion, about 29.3 kilometers per second, 1 kilometer per second faster at its closest approach to the Sun. This seems intuitive once you understand gravity. As the Earth gets closer to the Sun's gravity pulls more strongly, and the Earth falls a bit faster. As it recedes, gravity weakens, and it slows. But the deeper explanation, in terms of modern physics, is again conservation of angular momentum. Angular momentum is mass times velocity, times the distance from the center of rotation. If that quantity has to remain constant and the distance decreases, the velocity has to increase to compensate. Angular momentum conservation is why the Earth speeds up near the Sun and slows down far from it. The same principle that spins up a collapsing gas cloud into a protoplanetary disk. The same principle that accelerates water draining through a plug hole into a tighter and tighter spiral. Scale changes by orders of magnitude. The physics doesn't. Kepler's third law connected the orbital period of a planet to its distance from the Sun. Planets farther from the Sun take longer to orbit, and not just because they have more distance to cover. They also move more slowly. The relationship Kepler found is that the square of the orbital period is proportional to the cube of the average orbital radius. This was an empirical discovery, derived purely from observation, and Kepler published it in 1619, almost a decade after his first two laws. Newton later derived the same relationship from his laws of gravity and motion, showing that Kepler's third law wasn't a coincidence or a numerical pattern. It was a necessary mathematical consequence of how gravity works. Mercury, closest to the Sun, completes an orbit in 88 Earth days. Venus takes 225 days. Earth, 365 days. Mars, 687 days. Jupiter, almost 12 years. Saturn, almost 30 years. Neptune, 165 years. The farther from the Sun, the weaker the gravitational pull, the slower the orbital velocity, the longer the journey. By the time you get to Neptune, it moves at only about 5.4 kilometers per second. Neptune is so distant and slow that it had been discovered in 1846 before it had completed even one full orbit of the Sun. It finally completed its first observed full orbit in 2011, one Neptune year, observed from discovery to completion by human beings who lived and passed within that single planetary orbit. Kepler derived his three laws from observation alone, without any underlying physical theory explaining why the planets should behave this way. He knew what the planets did. He didn't know why. Newton provided the why 60 years later. Einstein refined the why further, 300 years after that. And in doing so, Einstein revealed something Newton couldn't have predicted. Now, here's something that unsettles most people the first time they encounter it. The Earth doesn't actually orbit the Sun. Not exactly. The Earth and the Sun both orbit a common center of mass called the barycenter. The barycenter is the point in a two-body system around which both bodies revolve. For the Earth-Sun system, the barycenter is located about 450 kilometers from the Sun's center. That's, well, inside the Sun. The Sun's radius is about 695,000 kilometers. So the Earth-Sun barycenter is a very small fraction of the way from the center to the surface. This means that for practical purposes, the Earth orbits the Sun, and the Sun barely wobbles. But technically, both are orbiting the barycenter. The situation gets more interesting when you consider the whole solar system. Jupiter is so massive, about 1,000th the mass of the Sun, that the Jupiter-Sun barycenter lies just outside the Sun's surface, about 50,000 kilometers above it. As Jupiter orbits, the Sun traces a small loop around this point. Saturn, Uranus, and Neptune add their own smaller contributions. The combined effect of all the planets makes the Sun's motion around the solar system's barycenter complex and irregular. The Sun traces a looping, wobbling path over the decades-long orbital periods of the outer planets. It weaves around, never quite returning to the same position, because the planets are never in exactly the same configuration, twice, not precisely, not on any accessible timescale. This solar wobble is the basis of one of the most powerful methods for detecting planets around other stars. When a planet orbits a distant star, it causes the star to wobble slightly. That wobble produces a tiny Doppler shift in the star's light, a periodic stretching and compressing of the light's wavelength as the star moves toward and away from us with the planet's orbital period. By precisely measuring that Doppler shift over time, astronomers can infer the presence of a planet, determine its orbital period, and calculate its minimum mass. The radial velocity method has confirmed hundreds of exoplanets. In every case, the principle is the same. Two bodies, orbiting their common center of mass. The same physics that applies to the Earth and the Sun applies to every planetary system we've ever found. Which means every planet we've discovered is being held in its orbit by exactly the same mechanisms as our own world. Everywhere we look in the galaxy, angular momentum and curved spacetime are doing the same work, running the same equations, producing the same result. Worlds in freefall, perpetually missing the thing they're falling toward. There's something else that holds the solar system together that's worth appreciating in its full scale. The Sun doesn't just hold the planets. It holds an enormous sphere of cometary material called the Oort cloud. The Oort cloud is a theoretical shell of icy bodies that extends from roughly 2,000 astronomical units out to perhaps 100,000 astronomical units or more. We've never directly observed an individual Oort cloud object. The Oort cloud's existence is inferred from the behavior of long-period comets. When a comet with an orbital period of millions of years appears, tracing a highly elongated orbit that takes it from deep in the outer solar system into the inner solar system and back out, astronomers can calculate backward along its trajectory to determine its origin. Almost always, the origin is the Oort cloud. The cloud was proposed by Dutch astronomer Jan Oort in 1950 after studying the orbital parameters of many long-period comets. He noted that the comets seemed to come from a roughly spherical distribution at enormous distances, not from any preferred direction, and concluded that a vast spherical cloud of icy objects must surround the solar system. The Oort cloud is so distant that sunlight, traveling at 300,000 kilometers per second, takes months to reach its inner edge and well over a year to reach the outer regions. The icy bodies in the Oort cloud orbit the Sun so slowly that a single orbit takes millions of years. Some of those bodies have never come close to the Sun at all. They've been on the outermost fringes of the solar system since the planets formed, drifting in the cold dark, essentially unchanged since the earliest days of the solar system. Occasionally, a passing star, or the galactic tidal force, the gentle gravitational gradient of the galaxy itself, sends one of them falling inward. It falls for millions of years, accelerating slowly. Then faster as it gets closer and the Sun's gravity grows. By the time it reaches the inner solar system, it's moving at tens of kilometers per second. Heat from the Sun vaporizes its ices. Gas and dust stream away from the nucleus. A coma and tail form. We call it a comet. Long-period comets are first-time visitors from the Oort cloud, following gravity-bent trajectories inward from the outermost reaches of the solar system. They carry information about the very early solar system. The composition of their ices and dust reflects the conditions in the outer protoplanetary disk 4.5 billion years ago, largely unchanged since then. The same gravitational principles govern their motion as govern the Earth's. They follow geodesics in curved spacetime. They conserve angular momentum. They fall and curve and sweep back out toward the outer solar system. If nothing perturbs them again on the return trip, they'll return on the same orbit millions of years from now, when whatever life exists on Earth will have no knowledge of their previous visit. The solar system is a gravitationally bound system at every scale. From the Earth's orbit to the outer edge of the Oort cloud, everything is held by the same force, expressed through the same mathematics. Let's pull the lens even closer now and look at what holds the Earth itself together. Because the Earth isn't just a rock floating in space. It's a structured world with a liquid outer core, a solid inner core, a thick mantle, and a thin crust. All of it held together by Earth's own self-gravity. The Earth's mass is enormous, roughly 6 times 10 to the power of 24 kilograms. That mass creates a gravitational field that pulls inward at every point on and in the planet. Every kilogram of rock and metal in the Earth is attracted toward every other kilogram. The result is that the Earth is approximately spherical. Gravity pulls everything toward the center of mass. Any protrusion, any mountain, any region that sticks up too high gets pulled back down. Mountains exist, but they exist at the limit of what rock can support against its own weight. The tallest mountains on Earth, Everest and its neighbors in the Himalayan range, are near the maximum height that rocky material can maintain before the rock at the base is under so much pressure that it flows like a very slow, viscous fluid over geological timescales. The crust of the Earth literally sinks under the weight of mountains, pressing down into the denser mantle beneath, like a boat settling into water. This is called isostasy. Mountains have deep roots of less dense crustal rock extending downward into the mantle, which buoy them up like the keel of a ship. Remove the mountain, and the root would gradually rise. This is what happens in places where ancient ice sheets melted at the end of the last ice age. Scandinavia is still rising today, slowly rebounding from the weight of kilometers of ice that pressed it downward tens of thousands of years ago. The land rises because the burden has been lifted, and the underlying mantle, which is more like a very slow fluid than a rigid solid on geological timescales, is flowing back to fill the space. This relationship between gravity and the strength of materials determines the shape of any rocky body. Small bodies, where gravity is weak, can have irregular shapes. Asteroids can be lumpy, elongated, even strangely angular, because their own gravity isn't strong enough to pull them into spheres. Large bodies, where gravity is strong, are forced into spheres by the inevitable victory of gravity over material strength. Earth, Mars, Venus, the gas giants, all roughly spherical, all shaped by the same inward pull of self-gravity. The boundary between irregular and spherical is approximately 500 kilometers in radius for rocky bodies. Below that size, a body may not have enough self-gravity to overwhelm the structural strength of rock and pull itself into a sphere. Above it, gravity wins, and the object inevitably rounds itself out. The Earth's interior is also structured by gravity in a very specific way. When the Earth was young, it was largely molten. The heat of formation, the energy from all those planetesimal impacts over tens of millions of years, was enormous. The kinetic energy of impacting bodies was converted to heat. Much of the early Earth was liquid, or at least partially molten. And when rocky material is liquid, gravity can sort it by density. Heavy materials, primarily iron and nickel, sank toward the center. Lighter materials, primarily silicates, floated toward the surface. This process is called differentiation, and virtually every large rocky body in the solar system has gone through it. The result is a layered Earth. A dense iron-nickel core at the center, about 12,000 kilometers in diameter. A mantle of silicate rock surrounding the core, about 2,900 kilometers thick. And a thin crust at the surface, between 5 and 70 kilometers thick, depending on whether you're under ocean or continent. The outer core is liquid iron and nickel at temperatures between 4,000 and 5,000 degrees Celsius. The inner core is solid iron and nickel at temperatures of roughly 5,000 to 6,000 degrees Celsius, actually hotter than the outer core, but kept solid by the immense pressure of the overlying mass. Pressure matters for the phase state of matter. At high enough pressure, even the hottest iron remains solid, because the pressure prevents the atoms from leaving their positions in the crystal lattice. This is why the inner core is solid, despite being hotter than the liquid outer core. The boundary between them is called the inner core boundary, and it's one of the sharpest seismic discontinuities in the entire Earth. When earthquakes occur, seismic waves pass through the entire planet. Different types of waves travel at different speeds through different materials. Some wave types, shear waves, can't travel through liquids at all. The absence of shear waves from certain directions and arrival time differences between different wave types tell seismologists about the state and composition of the Earth's interior. By studying how those waves bend, reflect, and are absorbed, scientists have mapped the interior of the planet in remarkable detail without ever drilling more than a tiny fraction of the way down. The deepest borehole ever drilled, the Kola Superdeep borehole in Russia, reached about 12 kilometers before the project was abandoned in the 1990s. That's roughly 2/1000ths of the way to the Earth's center. We know vastly more about the interior of the Earth from seismology than we ever could from drilling. The liquid outer core is important for reasons beyond just the Earth's internal structure. That liquid iron, convecting and circulating because of temperature differences between the hot inner core and the cooler lower mantle, combined with the Earth's rotation, generates the Earth's magnetic field through what's called the geodynamo effect. Electric currents flowing in the rotating liquid iron create a magnetic field that extends far above the atmosphere into space, forming a magnetic bubble called the magnetosphere. The magnetosphere deflects the solar wind, the continuous stream of charged particles flowing outward from the sun at speeds of around 400 to 800 kilometers per second. Without the magnetic field, the solar wind would gradually erode Earth's atmosphere, stripping away lighter molecules from the upper atmosphere over geological timescales. Mars almost certainly lost most of its early, thicker atmosphere this way. After its smaller iron core cooled and solidified, its magnetic field faded, and the solar wind was free to strip the atmospheric gases away into space. Today, Mars has an atmosphere less than 1% as dense as Earth's, composed mostly of carbon dioxide, utterly inadequate for life as we know it, and incapable of maintaining liquid water on the surface. Earth's magnetic field, generated by the liquid iron outer core, ultimately generated by gravity's sorting of dense material toward the center, is part of what makes the surface habitable. The magnetic field also creates the auroras, where charged particles from the solar wind funnel along field lines toward the polar regions, colliding with atmospheric molecules and causing them to glow. The aurora borealis and aurora australis are visible evidence of the magnetic shield protecting life below. The gravitational differentiation of the Earth's interior is therefore connected through a long chain of physical processes to the existence of liquid water at the surface, to the thickness of the atmosphere, and to the persistence of complex life over hundreds of millions of years. Gravity doesn't just hold the Earth in orbit. Gravity built the conditions for life. Let's take a moment to think about what an orbit actually feels like from the inside. Because one of the most profound things about being in orbit is what you don't feel. Astronauts aboard the International Space Station are in orbit around the Earth. They're moving at about 7.7 kilometers per second. They're about 400 kilometers above the surface, and they feel weightless. Not because there's no gravity. There absolutely is. Gravity at 400 kilometers altitude is about 88% as strong as it is at the surface. The astronauts are weightless because they're in freefall. They're falling toward the Earth. Their station is falling toward the Earth, but they're moving sideways so fast that they keep missing. They're in orbit, and in freefall, there's no sensation of weight. Weight is the sensation of being supported against gravity. When you stand on the floor pushes up against you. That push, the normal force, is what you experience as weight. In orbit, nothing is pushing up on you. You're falling freely, and you feel nothing. This is why long-duration spaceflight has such profound effects on the human body. Bones adapt to the mechanical forces placed on them throughout life. The skeleton exists partly to support the body against gravity. In microgravity, bones experience dramatically less mechanical stress, and the cells that build bone density reduce their activity, while the cells that break bone down continue working at roughly normal rates. Bones lose density over months in orbit. Muscles that normally work against gravity to keep you upright and moving atrophy from disuse. The cardiovascular system, calibrated to pump blood upward against gravity on Earth, redistributes fluid when there is no preferred up. Fluid shifts toward the head. The face becomes puffy. The legs become thin. Eyesight can change because the shifting fluid increases intracranial pressure and can compress the optic nerve or reshape the eyeball. These are real, documented consequences of removing the load that gravity imposes on the human body. Long-duration astronauts spend months rehabilitating after returning to Earth, relearning how to walk, rebuilding bone and muscle mass, readjusting to a world where gravity is constant and unavoidable. The Earth is in the same condition relative to the Sun as an astronaut in orbit around Earth. The Earth is in freefall around the Sun. Everything on and in the Earth is falling together at the same rate. The entire planet is in a state of orbital freefall. There's no sensation of falling because everything falls together. If you were somehow suspended in space, exactly in the Earth's orbit, but without the Earth around you, you would feel the same weightlessness. The Sun's gravity would be pulling you toward it, but your sideways velocity would carry you forward. You'd be in your own orbit, falling forever, never arriving. The Earth, in a profound sense, is a spaceship in perpetual freefall. It carries us through space, falling around the Sun, in a trajectory determined by the laws of physics built into the universe. We don't notice the fall because we're inside it. We've always been inside it. There's nothing unusual about it from where we're standing. Now, let's revisit Newton and Einstein one more time, because general relativity predicts effects on orbits that Newton's theory doesn't. For most planets in our solar system, these effects are so small as to be negligible. But for Mercury, the planet closest to the Sun, where the gravitational field is strongest, the relativistic effects are measurable. Newton's theory predicts that a planet in a perfectly two-body system, just the Sun and the planet alone, should trace a closed ellipse. The ellipse should close perfectly on itself each orbit. The perihelion, the closest point to the Sun, should return to exactly the same position each time. But Mercury's perihelion doesn't quite close. Each orbit, the ellipse precesses slightly. The perihelion shifts forward by a tiny angle. Most of this precession can be explained by the gravitational influence of the other planets, particularly Jupiter. But about 43 arc-seconds per century remained unexplained within Newton's framework. For decades in the 19th century, this discrepancy puzzled astronomers. Some proposed that there was an undiscovered planet closer to the Sun than Mercury, whose gravity was causing the anomaly. They even named it Vulcan. Expeditions were mounted to look for it during solar eclipses, when planets near the Sun would be visible in the darkened sky. Tentative sightings were reported by amateur astronomers, but no confirmed planet was ever found. When Einstein published general relativity in 1915, he immediately applied it to Mercury's orbit. The calculation was exact. General relativity predicted precisely 43 arc-seconds per century of perihelion precession from the curvature of spacetime near the Sun. Not approximately. Exactly. The match was so perfect that Einstein later described it as one of the greatest joys of his scientific life. It wasn't just that general relativity solved a long-standing mystery. It was that it predicted exactly the right number without any free parameters, without adjusting anything to fit the data. The theory worked. Mercury's orbit is slightly different from what Newton predicted because space-time near the Sun is actually curved. And Mercury is close enough and fast enough to feel that curvature in a measurable way. Every orbit around the Sun has a tiny relativistic contribution to its precession. For Earth, the relativistic precession is about 3.8 arc-seconds per century, much smaller than Mercury's, because Earth is farther from the Sun, where the curvature is gentler. For GPS satellites orbiting Earth, relativistic effects on time are actually large enough that they have to be corrected for continuously. GPS satellites are moving fast relative to observers on Earth's surface, which causes their clocks to run slightly slow due to special relativistic time dilation. But they're also higher in Earth's gravitational field, where space-time is less curved, which causes their clocks to run slightly fast due to general relativistic effects. The two effects partially cancel, but not completely. The net result is that GPS satellite clocks gain about 38 microseconds per day relative to clocks on the surface. If you didn't correct for this, the position errors in GPS systems would accumulate at about 10 kilometers per day. Within hours of ignoring the relativistic correction, GPS navigation would be useless. Relativity isn't abstract physics reserved for extreme conditions. It's running on consumer electronics worldwide, every day, keeping navigation systems accurate. There's one more thing to understand about what keeps the Earth in its orbit over the very long run. Orbits in the real solar system aren't forever. The solar system is not a perfectly isolated, perfectly conservative system. Energy is slowly leaking away. The mechanism is gravitational radiation. Every orbiting body emits gravitational waves, tiny ripples in spacetime caused by the constantly changing distribution of mass as bodies orbit each other. For the Earth-Sun system, these gravitational waves carry away an utterly negligible amount of energy. The orbit shrinks by a few centimeters over the entire age of the universe due to gravitational wave emission. It is, for any practical purpose, zero. But the principle matters, because for compact systems, like binary neutron stars or binary black holes orbiting close to each other, gravitational wave emission is enormous. Binary pulsars, pairs of neutron stars orbiting each other, have had their orbital decay measured with extraordinary precision. The rate at which they're spiraling together due to gravitational wave energy loss matches the predictions of general relativity to better than 1%. The first such system, discovered in 1974 by Russell Hulse and Joseph Taylor using the Arecibo radio telescope, provided the first indirect confirmation that gravitational waves exist and carry energy, exactly as Einstein's theory predicted. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. 2 decades later, LIGO detected gravitational waves directly for the first time. For the Earth-Sun system, this effect is irrelevant on any human timescale. The Sun will have expanded into a red giant and dramatically reshaped the inner solar system long before gravitational wave emission has any measurable effect on Earth's orbit. But the fact that orbits in general are not eternal, that they slowly radiate energy and spiral together, is a reminder that the laws of physics don't make exceptions. Everything is temporary. Every gravitationally bound system eventually merges, on timescales that dwarf the current age of the universe for most systems. But eventually, the Earth's orbit is stable on any timescale relevant to life, civilization, or anything we might build or become. But in the very long run, on the timescale of physics rather than history, nothing orbits forever. There is one last piece of this that ties everything together. Something that sits beneath the orbit, beneath the angular momentum, beneath the curvature of space-time. Something more fundamental than all of it. The question of why gravity exists at all. Why does mass bend space-time? What is the mechanism at the deepest level? Newton described gravity with equations and explicitly declined to speculate on the underlying cause. His famous phrase was hypotheses non fingo, which translates roughly as I frame no hypotheses. He meant that he was describing what gravity does, not claiming to know what it is. Einstein replaced the force with geometry. But even Einstein's description of curved spacetime is a description, not an explanation at the deepest level. It tells us how mass and spacetime interact. It doesn't tell us why. In the current framework of physics, gravity is one of the four fundamental forces. The others are electromagnetism, the strong nuclear force, and the weak nuclear force. Three of those four forces have been successfully described by quantum field theory, the framework in which forces are mediated by particles. Electromagnetism is mediated by photons. The strong force is mediated by particles called gluons. The weak force is mediated by the W and Z bosons. Gravity, in this picture, should be mediated by a particle called the graviton, a massless particle, like the photon, traveling at the speed of light, carrying gravitational influence across space. The graviton has never been detected. It probably never will be, at least not with any technology we can conceive of. Gravitons interact so weakly with matter that detecting a single one would require a particle detector, roughly the mass of Jupiter, operating for decades. That's not a practical experiment. And no one has successfully combined quantum field theory with general relativity into a single consistent theory. The two frameworks, quantum mechanics, governing the very small, and general relativity, governing the large, are both extraordinarily successful in their own domains. They make predictions that match experiment with incredible precision. But they don't speak the same mathematical language. When you try to apply quantum mechanics to gravity at the Planck scale, the scale at which quantum gravitational effects should become significant, you get mathematical infinities that won't cancel out. The equations produce nonsensical predictions. Something is missing. String theory, loop quantum gravity, and various other approaches have been proposed to bridge the gap. String theory replaces point particles with one-dimensional vibrating strings and requires extra dimensions of space curled up at scales too small to observe. Loop quantum gravity quantizes space-time itself into discrete chunks at the Planck scale, the smallest, meaningful length at which classical concepts of space and time break down. Neither has yet been confirmed experimentally. Neither makes predictions that are currently testable with the instruments we have. The deepest question in all of physics, why does gravity work the way it does at the quantum level, remains open. What we know is what it does. It curves space-time. It holds the Earth in its orbit. It built the solar system from a collapsing cloud of gas. It structures the galaxy. It binds clusters of galaxies into the largest gravitationally held structures in the observable universe. And it's the reason you can stand on solid ground and look up at a sky full of stars without floating away. The mechanism behind it, the deepest why, is one of the great unsolved problems in science. The fact that we can describe gravity with extraordinary precision, predict it accurately enough to navigate spacecraft across billions of kilometers, use it to time satellites circling overhead, and detect its waves arriving from black holes more than 1 billion light-years away, while still not fully understanding its quantum nature, is one of the stranger aspects of modern physics. We can calculate the Earth's orbit to extraordinary precision. We cannot explain, at the deepest level, why mass curves space-time. That's where we are, comfortable in our ignorance of the deepest layer, productive despite it. There's a dimension to the Earth's position in space that rarely gets discussed when people think about orbits. The Earth isn't just in any old orbit. It's in an orbit in a specific part of the galaxy. And the part of the galaxy we happen to occupy matters more than most people realize. The Milky Way, like all large spiral galaxies, has a structure that isn't uniform. It has a dense central bulge packed with billions of old stars and at least one supermassive black hole. It has spiral arms, regions of relatively higher star density where star formation is actively occurring. And between the arms are inter-arm regions, quieter zones where star density is lower and star formation is slow. The Sun sits in one of these inter-arm regions, in the Orion arm, sometimes also called the Orion Cygnus arm. We're not deep inside a dense spiral arm. We're in a relatively quiet neighborhood. This matters. Dense regions of the galaxy are more dangerous. More stars mean more supernovae, which produce bursts of radiation capable of stripping away atmospheres and altering the chemistry of planetary surfaces. More stars mean more close stellar encounters, gravitational interactions that could perturb orbits. The outer regions of the galaxy have a different problem. Fewer of the heavy elements produced by stellar nucleosynthesis. Out near the edge of the galactic disk, stars are mostly hydrogen and helium. The rocky planets we find around those stars tend to be smaller, less massive, less chemically diverse. The galactic habitable zone, the region of the galaxy where conditions are favorable for complex life, is thought to be a ring roughly centered on our position. Far enough from the dangerous galactic center, close enough to the galactic center to have access to heavy elements, not so far out that heavy elements become scarce. The Sun sits squarely in this zone. Whether that's coincidence or selection effect, we can't say. We're only here to notice it because the conditions allowed us to evolve. That's called the anthropic principle. It doesn't explain anything. But it does remind us that the Earth's position in the galaxy is part of the same question as the Earth's position in the solar system. Both are the result of the same chaotic, historical, contingent process that produced, among billions of other outcomes, a solar system in the right part of a galaxy, with a planet in the right part of the solar system, with conditions that allowed chemistry to become biology. The full answer to what holds the Earth up in space extends from the quantum level to the cosmological level. From the graviton we haven't detected to the large-scale structure of the observable universe. Every layer connects. Let's also consider what happens at the edges. The solar system doesn't end cleanly. There's no wall, no line in space where the Sun's gravity stops and interstellar space begins. The Sun's gravitational influence fades gradually with distance. Out to the Oort cloud, hundreds of thousands of astronomical units away, the Sun still holds icy bodies in very slow orbits. Beyond that, the boundary between the Sun's gravitational domain and the rest of the galaxy is fuzzy. It's defined roughly by the point where the Sun's gravity is comparable to the tidal force of the galaxy itself, the gentle gravitational gradient across the galaxy that can nudge objects. This boundary is called the Hill sphere of the Sun, sometimes the Roche sphere. For the Sun, the Hill sphere extends to roughly 1 to 2 light-years in radius, the inner edge of the Oort cloud's most distant regions. Beyond the Hill sphere, objects are no longer gravitationally bound to the Sun. They're bound to the galaxy. Interstellar space isn't empty. It contains very thin gas, mostly hydrogen and helium, dust grains, cosmic rays, high-energy charged particles accelerated by supernova shockwaves and other energetic events, magnetic fields permeating the galaxy, and the occasional rogue object, a planet or a comet or an asteroid, flung out of its home solar system by a gravitational interaction. In 2017, astronomers detected the first confirmed interstellar object passing through the solar system. They named it Oumuamua. It was moving far too fast to be in any bound orbit around the Sun. Its trajectory was hyperbolic. It came from somewhere outside the solar system, passed through, and departed. Its origin is unknown. Its shape was unusual, elongated in a way no solar system object quite matches. The slight excess acceleration it showed, beyond what solar radiation pressure alone could explain, generated considerable discussion. Most researchers believe it was a strange but natural object, perhaps a fragment of a frozen nitrogen glacier from another planetary system. A few years later, in 2019, a second interstellar object was detected. This one, named Borisov, was more clearly a comet with a gas coma and tail that formed as it warmed near the Sun. These interstellar visitors are not held up by anything. They're not bound to the Sun. They pass through like ships through a port, pulled briefly by the Sun's gravity and then released. Their trajectories remind us that the solar system is not isolated. It's embedded in the galaxy, occasionally receiving visitors from the wider stellar neighborhood. The boundary between here and there isn't a wall. It's a gradient. There's something else worth appreciating about what the Earth's orbit means in the context of time. The Earth is 4.5 billion years old. The Sun is about the same age. They formed together from the same cloud of gas and dust. The Earth has been in roughly its current orbit for almost its entire history. It has completed roughly 4.5 billion orbits of the Sun. Each orbit, 365 days. Each day, one rotation. Each rotation, thousands of kilometers traveled through space. In 4.5 billion years, the Earth has traveled a distance that would take light roughly 3,000 years to cover. All of that motion, sustained for billions of years, without any engine, without any fuel, without anything wearing out. Just the geometry of spacetime and the conservation of angular momentum. No technology we have built lasts more than decades without maintenance. No structure we have made has survived millions of years intact. But the Earth's orbit needs nothing. It requires no upkeep. It will run without maintenance for as long as the Sun exists, and no major perturbation disrupts it. That's not just impressive. It's a fundamentally different way of understanding what things can be. An orbit isn't a mechanism that runs. It's a state that persists. The difference is everything. Mechanisms wear out. States persist until something changes them. The Earth's orbit is a state. a condition defined by the angular momentum the Earth has and the mass of the Sun. Change either of those, and the orbit changes. Leave them alone, and the orbit runs indefinitely. This is why orbital mechanics is so useful for long-range planning. Launch a spacecraft in the right direction with the right speed, and you can predict where it will be decades from now. The Voyager probes, launched in 1977, are now nearly 50 years into their journey beyond the solar system. No one is steering them. No engines are running. They're following the trajectories set for them at launch, modified slightly by the gravitational influences of the planets they passed, traveling now through interstellar space on trajectories that can be calculated to reasonable precision without any additional information. Just Newton's laws. Just the initial conditions. Just the state that was set and left to run. The Earth is doing the same thing. It was set in motion 4.5 billion years ago and left to run. And it has been running ever since. Now, there's one more layer that most people never think about. The question of what keeps the Sun itself where it is. Because the Sun isn't stationary either. We've already mentioned that the solar system orbits the center of the galaxy. But even within that orbital motion, the Sun bobs up and down relative to the galactic plane. The Milky Way is a flattened disk. Most of the galaxy's mass is concentrated near the midplane of the disk. The Sun's orbit isn't perfectly in the midplane. It oscillates above and below the plane as it travels around the galaxy. The period of this vertical oscillation is roughly 60 to 90 million years. The Sun passes through the galactic midplane, where star density is highest, approximately every 30 to 45 million years on each crossing. These passages through the denser midplane might be associated with increased cometary bombardment of the inner solar system, as the galactic tide is stronger there and more effective at perturbing the Oort cloud. Some researchers have suggested a connection between the Sun's midplane crossings and periodic mass extinctions in Earth's geological record. The evidence is suggestive, but not conclusive. The statistical case for a strict periodicity in extinctions has been challenged repeatedly. What's clear is that the Sun's position relative to the galactic plane changes over time, and this changing position exposes the solar system to varying levels of radiation, cosmic rays, and gravitational perturbations from the dense galactic environment. The Earth's environment, over geological and astronomical timescales, is not just determined by its orbit around the Sun. It's determined by the Sun's orbit around the galaxy. Everything is in motion. Everything is embedded in larger motions. The hierarchy of orbits and gravitational influences extends from the nucleus of the Earth outward to the largest structures in the observable universe. Let's also spend a moment with the idea of orbital resonances. Because they're one of the stranger ways that gravity shapes the solar system, and they're directly relevant to the stability of the Earth's orbit. A resonance occurs when two orbiting bodies have orbital periods that form a simple numerical ratio: 2 to 1, 3 to 2, 4 to 3. When two bodies are in resonance, they regularly return to the same configuration, the same relative positions. Each time they do, they exert gravitational forces on each other in the same direction. These repeated nudges can add up over time. Some resonances are stabilizing. They lock two bodies into a configuration where they're always at a safe distance from each other when they're in the same region of space. The orbital resonance of Pluto with Neptune is of this type. Pluto and Neptune are in a 3-to-2 resonance. Pluto completes 2 orbits in the time Neptune completes 3. Because of the way the resonance works, every time Pluto is closest to the Sun in its orbit, Neptune is always far away from that location. They never come close to each other, despite Pluto's orbit crossing Neptune's orbit on a diagram. The resonance protects them both. Other resonances are destabilizing. They repeatedly push a body in the same direction, amplifying small perturbations over time until the orbit becomes chaotic or the body is ejected entirely. The gaps in Saturn's ring system, called Kirkwood gaps in the asteroid belt and Cassini division in Saturn's rings, are cleared out by destabilizing resonances with Saturn or specific inner moons. Any small body that strays into those resonance zones gets its orbit gradually amplified until it's kicked out. The Earth isn't currently in any strong orbital resonance with another planet. But the subtle gravitational interactions between all the planets create what's called a secular resonance structure in the inner solar system. Slow variations in orbital parameters interact with each other over millions of years. Mathematicians and planetary scientists have found that the Earth's orbit is technically chaotic on timescales of tens of millions of years. Not unstable, but unpredictable in detail. If you tried to simulate the solar system forward millions of years with a computer, tiny errors in the initial conditions would grow into large differences over that timescale. This is the chaotic nature of the gravitational few-body problem. When more than 2 bodies interact through gravity simultaneously, the equations cannot be solved in closed form. Numerical simulations can track the system for a while, but errors accumulate. The detailed future configuration of the solar system millions of years from now is fundamentally uncertain. But the range of possible futures is bounded. The Earth will stay in a roughly similar orbit. The planets will stay in roughly similar orbits. The system won't fly apart. The chaotic nature of the dynamics doesn't threaten the long-term existence of the solar system. It just means we can't know the exact configuration far in advance. That's a lesson that applies more broadly than planetary science. Chaotic systems aren't necessarily dangerous. They're just unpredictable in detail. Stability and predictability are different things. The Earth's orbit is stable, but it is not, in the strictest mathematical sense, predictable indefinitely. Let's take one final look at the question from the perspective of what would actually have to happen to disrupt the Earth's orbit. Because understanding what would change the orbit is another way of understanding what's maintaining it. To significantly change the Earth's orbit, you'd need to add or remove angular momentum from the Earth. That requires an external gravitational force, with a component perpendicular to the Earth's current velocity. A large asteroid or comet impact would do this. The energy delivered by a very large impactor would change the Earth's velocity slightly. But to significantly alter the orbit, you'd need an impactor of enormous mass. The Chicxulub impactor that contributed to the end Cretaceous extinction was about 10 to 15 kilometers across. It caused global devastation. It altered the climate for years, but it barely budged the Earth's orbit. The mass ratio between the Earth and even a very large impactor is so extreme that the orbital change is tiny. To meaningfully alter the Earth's orbit through an impact, you'd need an object approaching the mass of a small moon. That would be a civilization-ending event on a completely different scale. A close stellar encounter would also change the Earth's orbit. If a star passed near enough to the solar system, its gravity would perturb the planets. Stars do occasionally pass close to the solar system. The closest known future stellar encounter is a red dwarf called Gliese 710, which is expected to pass within about 0.064 parsecs of the Sun, closer to us than Proxima Centauri is today. That will happen in about 1 million years. At that distance, the gravitational perturbation to the solar system will be modest. It might shake loose some Oort cloud comets, but it won't significantly alter the planetary orbits. For a stellar encounter close enough to meaningfully alter the Earth's orbit, you'd need a star to pass within the inner solar system. That would be an extraordinarily rare event. The density of stars in our part of the galaxy and the speeds at which they move relative to each other makes such an encounter unlikely over the remaining lifetime of the Sun. The Earth's orbit is robust. Not fragile. Not teetering. Robust. The forces that could meaningfully alter it are large, rare, and largely avoidable. The forces that maintain it, angular momentum conservation and the curvature of space-time, are fundamental and require nothing. There's a framework that ties all of this together, one that physicists rarely explain to general audiences because it's abstract, but that illuminates the whole picture in a way nothing else does. Everything we've talked about, angular momentum, curved space-time, orbital stability, all of it is a consequence of something deeper. Symmetry. The laws of physics are symmetric in certain ways. They look the same in every location in space. That spatial symmetry is the reason momentum is conserved. They look the same at every time. That temporal symmetry is the reason energy is conserved. They look the same in every direction. That rotational symmetry is the reason angular momentum is conserved. These aren't separate rules added on top of the physics. They're consequences of the geometry of the universe. Emmy-Noether's theorem makes this precise. Every continuous symmetry of the laws of physics corresponds to a conserved quantity. This is one of the most profound results in all of mathematics and physics. It means that conservation laws aren't separate postulates. They're built into the structure of reality at the level of symmetry. The universe is symmetric in rotation. Therefore, angular momentum is conserved. Therefore, the Earth cannot simply stop moving sideways. Therefore, the Earth orbits. That chain of reasoning goes from the abstract structure of the universe down to the specific motion of a planet. The Earth's orbit is not an accident or a coincidence. It's a consequence of the universe being rotationally symmetric. It's as close to inevitable as anything in physics gets. The fact that you exist to observe it, that there's an Earth with stable conditions long enough for biology to arise, develop, and ask why the Earth orbits, is far more contingent. That part required the right initial conditions, the right stellar history, the right location in the galaxy, the right protoplanetary disk, the right collision to produce the Moon. The orbit itself required only that the laws of physics be rotationally symmetric, which, as far as anyone has ever measured, they are. Now, let's also take a moment with dark matter, because it's relevant to the Earth's orbit in an indirect but real way. The orbits of stars in the Milky Way don't match what you'd expect based on the visible matter alone. Stars at the outer edges of the galaxy orbit too fast. They should be moving slowly, like Neptune moves slowly because it's far from the Sun's gravity. But they're not. They're moving at speeds that can only be explained if there's far more mass in the galaxy than we can see. This invisible mass is called dark matter. It doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all. It interacts only through gravity. And there's a lot of it. The Milky Way contains roughly 6 times as much dark matter by mass as visible matter. The dark matter is distributed in a roughly spherical halo surrounding the entire galaxy, extending far beyond the visible disk of stars. The solar system is embedded in this dark matter halo. Dark matter is passing through the Earth right now. Billions of dark matter particles are moving through your body every second, completely undetected, interacting with your atoms so weakly that detecting a single interaction requires enormous underground detectors. The dark matter halo contributes to the gravitational potential that the solar system orbits within. It affects the long-term trajectory of the Sun around the galaxy. And in very subtle ways, it might affect the Oort cloud and the long-term evolution of the solar system's environment. The effect on the Earth's orbit directly is negligible. Dark matter density in the solar system is extremely low, roughly 10 to the power of -25 kilograms per cubic meter. The gravitational effect of that density on anything orbiting the Sun is far below any detectable or significant level. But the fact that dark matter is part of the gravitational structure the solar system exists within is worth knowing. The universe contains far more than we can see, and that invisible majority is part of what holds the large-scale structure of the galaxy together. It's part of the architecture within which the Earth orbits. Even questions as simple as what holds the Earth up led, eventually, to the edges of what we know. One thing that's worth sitting with is how recent all of this understanding actually is. The idea that Earth orbits the Sun, rather than the other way around, was controversial in Europe until the 1700s. Galileo was tried for supporting it in 1633. He was forced to publicly recant the heliocentric model and was placed under house arrest for the rest of his life. The idea that gravity was a universal force, not just something that made objects fall on Earth, but the same force that kept the Moon in orbit and the planets around the Sun, was Newton's, published in 1687, less than 350 years ago. The idea that gravity is geometry, that mass bends spacetime, that orbits are geodesics in curved spacetime, was Einstein's, published in 1915, 110 years ago. The first detection of gravitational waves, confirming one of the most dramatic predictions of general relativity, was 2015. Within living memory, the first image of Sagittarius A itself, the black hole at the center of our galaxy, whose gravity holds the Milky Way together, was taken in 2022. The understanding we have of what holds the Earth up is not ancient wisdom. It's a recent achievement, built step by step over the last few centuries by people who were willing to trust observations over inherited assumptions. Kepler trusted Tycho's data over the ancient assumption of circular orbits. Newton trusted the mathematics over the common-sense idea that the moon and the apple should be governed by different rules. Einstein trusted the mathematics over the intuition that space and time were separate, absolute things. Each step required abandoning something comfortable for something stranger and more accurate. The story of how we came to understand the Earth's orbit is also the story of how science works. Not through sudden genius alone, though genius played a role, but through accumulation. Observation, building on observation. Theory, refined by experiment. Each generation inheriting the framework built by the previous one and finding the cracks, the anomalies, the things that don't quite fit, and using those cracks as the entry point for deeper understanding. Mercury's perihelion precession was a crack. The anomalous speeds of outer galactic stars was a crack. Both led to new physics. Both expanded the picture. Both added layers to the answer to the question of what holds the Earth up in space. The current picture is extraordinarily detailed and well-tested, but it has its own cracks. Dark matter is the most prominent. We know it's there from its gravitational effects. We don't know what it is. The quantum theory of gravity is another. We know general relativity and quantum mechanics both work. We don't know how to combine them. These cracks are not embarrassments. They're invitations. The next generation of physicists will find the framework that explains them, just as Einstein found the framework that explained Mercury's orbit. And when they do, the answer to what holds the Earth up will get even deeper, even more surprising, even more beautiful. Let's return to the central question one final time with everything we now know. What is actually holding the Earth up in space? The word up is doing something deceptive. It implies that there's a down, a floor, a surface below the Earth that it might fall toward. There isn't. Down, from Earth's perspective in its orbit, is toward the Sun, and the Earth is moving too fast sideways to fall into it. The Earth is held in its current trajectory by the curvature of spacetime created by the Sun's mass, carrying it around in a nearly circular geodesic. It's retained in that trajectory by the conservation of angular momentum, a law of physics so fundamental that it emerges directly from the rotational symmetry of the universe itself. It's stable because the orbit is a stable equilibrium, self-correcting against small perturbations. It's tilted and spinning because of the angular momentum delivered by billions of years of impacts, and ultimately inherited from a slowly rotating cloud of interstellar gas 4.5 billion years ago. It's at the specific distance from the Sun that it is because of where, in the protoplanetary disk, the conditions were right for rocky material to accumulate, and because of where the gravitational reshuffling of the outer planets left it after the solar system settled. The Moon is there because of a catastrophic impact, and that moon stabilizes the axial tilt and slows the rotation, both of which influence the long-term climate stability that made complex life possible. The magnetic field that shields the surface from solar wind exists because gravity differentiated the Earth's interior, sinking iron to the center, where it drives convection that generates the field. Nothing holds the Earth up. The concept doesn't apply. The Earth is moving through curved spacetime, conserving its angular momentum, tracing a path determined by physics so fundamental it's written into the structure of the universe itself. We are passengers on a falling world, falling endlessly around a star that is itself falling, around the center of a galaxy that is falling toward a neighbor galaxy, all of it embedded in the expanding fabric of a universe that has been running this way since the very beginning. There is no flaw. There never was. The next time you look up at a clear night sky and watch the stars hold their positions above you, know that none of them are still. Every one of them is moving. Every one of them is orbiting something. Every one of them is falling. The Earth beneath your feet is falling too. It always has been. It's just that the geometry of spacetime and a conserved quantity called angular momentum ensure that the falling never ends. That's not a problem to be solved. It's not a balance being actively maintained by something. It's just what the universe does with mass and motion and time. It builds worlds. It keeps them going. And it carries us, without our asking, through 4.5 billion years of night. Good night.